Hello everyone, and welcome back. Today we're going to be continuing our journey through the exploration of definite integrals and look at some very important fundamentals that you definitely should know when dealing with integration of continuous or almost continuous functions. So let's look at a couple properties that we've already built up to this current moment. So the integral from a to b of f of x dx, we already know even if we cannot find exactly what it is, we can always approximate it with a variety of methods. Left endpoint, right endpoint, midpoint, trapezoidal, Simpson's rule, and so on, provided that the function is continuous on that interval AB. For now, this assumption is going to be very important. Also, we proved that for particular types of functions, in particular monomials or polynomials, we can actually integrate polynomials and get another polynomial back of 1 degree higher, just sort of scaled by this little constant, 1 over n plus 1. Provided that, of course, n is not equal to 1, or minus 1, or minus 1 in this case. So constants, as we've already proven, can be factored out outside the integral, giving us the constant multiple of the original integral, and integrals can distribute over sums and differences of continuous functions. So let's just do a quick review example, just in case you have forgotten how these things work together. Suppose we have the integral from 1 to 3 of x minus 4x squared plus 5. And don't forget your dx. So what I'm going to do is I'm going to distribute my integral over sums and differences of functions and factor out my scalars. Once I do that, I'm going to have the integral from 1 to 3 of x dx minus 4 times the integral from 1 to 3 of x squared, and then plus 5 times the integral from 1 to 3 of 1. Some people will just write that as dx. So once I have that, this is going to be equal to 1/2 x squared minus 4/3 x cubed plus 5x, and then we're going to evaluate this as x goes to 3, as x goes to 1, and then subtract. So when I plug in x is equal to 3, I'm going to have 3 squared, which is equal to 9 divided by 2, minus 3 cubed, which is 27, and 27 times 4 is something. I'll just write that as 27 times 4. And then here we have 5 times 3, which is going to be equal to 15. And then minus 1/2 minus 4/3 plus 5 is what you get when you substitute 1. So once you do all that math, and you make sure you don't do any simple mistakes, you're going to get minus 62 over 3, and that will be your definite integral. So what does this even mean? Because I thought integrals represented areas in the curves. Why do I have a negative number here? So integrals on the curves represent area in some sense, but you have to keep in mind that there's no restriction on what the integral can come out to. It can come out to 0, it can come out to positive numbers, or even negative numbers too, and sometimes even infinite quantities. So when you're looking at integrals, you have to keep this in mind. Let's assume that we have a function like sine and cosine, which goes above the x-axis and below the x-axis on some different subintervals. So let's give this a name, for example, A. This point, let's assume that's B. And let's assume that this is point C. And let's assume that this is our function f on this x-axis, where y values are our f of x values. So this first area, in particular from A to B, this is our intuitive picture for areas in our curves. In this sense, since we see that the integral from A to B is a positive number, what you should actually be interpreting this as is it's mostly above the x-axis. That's what positive definite integrals actually represent in this context. And if we look at our integral from a to b, or actually no, let's not go from a to b, let's go from b to c. So b to c of f of x dx. And since we have that this is mostly, in this particular case always, below the x-axis, then what we're going to have is that this is going to be equal to a negative number. Now there are some special cases, but in both of these cases, A must be less than B for this to be appropriate, and B must be less than C for this to be appropriate. So keep those subtle little things in mind, because we have to traverse across this x-axis from left to right in order for these interpretations to be accurate and also appropriate. Now, when you sort of go backwards, you get what is called the limit reversal rule. So limit reversal rule. And it says this. Suppose that you want to traverse an interval from b to a where b is bigger than a. Then what you can do, and you can use this, do this proof via Riemann sums, where you're actually going to get is minus 1 times the integral from a to b of f of x dx. So if we look at a particular example, where we go, for example, the integral from 1 to 2, let's do 2x, which is pretty easy. So that's going to be x squared for x goes to 2, and as x goes to 1. That's going to be 4 minus 1, which is 3. And if we go from the integral from 2 to 1 of 2x dx, which is still going to be x squared, but instead of 1 to 2, we're going to go from 2 to 1. So that's going to be equal to 1 squared minus 2 squared, which is 4, so that's minus 3. Notice that when I reverse those limits, the only real thing that's going to swap is going to be those things. So that means this is going to be equal to the opposite of 4 minus 1, which is going to be equal to the opposite of the integral from 1 to 2 of our 2x dx function, which is just going to be equal to minus 3, of course. Right? So if you reverse your limits, the only thing that changes with your definite integral value is just the sign. Now, there are a couple other little cute properties that you definitely should know when working with definite integrals, and especially when you have symmetry on symmetric intervals. Symmetric about 0 intervals. All right. Of course, you can generalize it about, any vertical axis of symmetry besides x equals 0, but x equals 0 is the universal one, at least for most cases. So what we have here, let's assume that f is an even function, i.e. f of minus x equals f of x for all x in its domain. A very simple function, or not necessarily simple, is the function f of x is equal to the sine x over x. If we glue in that removable discontinuity at 0, we can extend this to the sinc function. So what does the sinc function look like? So you might remember this as it's almost like a sine wave, but it sort of dampens as you go to infinity. So it's a wiggly sine wave that dampens on the tails. So that's our sinc function. Notice that it is symmetric about the y-axis. Symmetric about y-axis. That's usually what we refer to as an even function, right? And you can verify that it's even by substituting minus x. So we have sine of minus x over minus x. And sine of minus x is an odd function, so that means negative can factor out of it. And then we have those two minus signs, which is going to cancel. So we have that this is precisely equal to our original function, f of x. So f of minus x is equal to f of x, provided that x is not equal to 0, or with the sinc function where it's defined as 1, we still have that it is true. Therefore, we have that the sinc function is an even function. Now, what can you say about the area under the curve for even functions? Notice that on the left, we have some area, like in that little region, and we have on the right, this little area in the blue region. Since it's symmetric about the y-axis, the areas should also be symmetric too. So that means if we go from, say, minus infinity to 0 of this particular function f of x, you're actually going to get the integral from 0 to infinity of f of x. They're precisely the same thing since they're mirror images, about x is equal to 0 actually. And you can also say that the integral from minus infinity to infinity, the entire thing, can be found by just doing 2 times the integral from one of those things. Here I'm choosing 0 to infinity, but you could choose minus infinity to 0 if for some reason you believe that that integral is a little bit more easier to deal with. Another case of symmetry would be odd symmetry. So an odd function is where you have f of minus x equals the opposite of f of x. And let's assume this is true for all x in the domain of that particular function f. So if that's the case, let's actually look at a particular example f that makes this true. Let's do x plus the sine of x all over x squared plus 1. So if we plug in minus x here, we're going to have minus x plus the sine of minus x all over minus x squared plus 1. So on the top, we're going to have minus 1 times x plus minus 1 times sine, since sine is odd. And on the bottom, minus something squared is the same as something squared, so we have just x squared plus 1. So notice that we can factor out that minus 1 out of the top, leaving us with x plus the sine of x. The bottom hasn't changed, and that's just going to equal to minus f of x. So we have that f of x, or f of minus x, is equal to minus f of x for all x in the set of real numbers, which in this case is r. Therefore, f is odd. So what's so special about integrals on odd functions? Well, if we look at a particular odd function, sine, for example, where if this is the sine function, here this is going to be equal to pi, and this is going to be equal to minus pi. If you look at the area here and the area here, they're the same but opposites, right? Because that's going to be a positive integral, that's going to be a negative integral, but they're symmetric about the origin, so they should be equal but opposite values. So when we integrate from minus pi to pi, for the sine function, even though we may not know what that integral actually is from 0 to pi or minus pi to 0, it should be equal to 0. In particular for our example, because the integral of sine is actually going to be pretty easy, but the integral from, say, minus 2 to 2 of this function x plus the sine of x all over x squared plus 1, this integral is a little bit more complicated to deal with, but since we've already proven that this function f is an odd function, and our integral is on a symmetric domain about x is equal to 0, that means that integral is 0 as well, which is actually very, very nice. Now, another little side or subtle note, in case you haven't realized, is the following. If we have the integral from a to b of f of x dx, this represents in some sense, again, the area underneath the curve. So this is actually just a number. So if somebody tries to be a little bit fancy and says, well, what is the derivative of the integral from 5 to 7 of e to the minus x squared dx? Now you may be stuck up on the question, well, what is the exact area underneath e to the minus x squared from 5 to 7, right? And if you don't know what e to the minus x squared looks like, it almost looks like a bell curve. And you're like, well, that seems like a very difficult integral to solve, but it doesn't really matter. It's just a number, and the derivative of numbers are 0, right? Regardless of what that number is, right? And another little note that I want to mention is that since it is a number, it doesn't really matter what variable we really put here, as long as we're consistent about it. So if we have the integral from a to b of f of x dx, you can use other variables too. For example, the integral from a to b of f of y dy. You can use the integral from a to b of f of t dt. You can use the integral from a to b of f of u du. And you could even be a little bit more fancy. For example, you can do the integral from a to b of f of x squared dx squared. You can also do the integral from a to b of f of sine of x d sine of x. As long as they're the same, they're all equivalent. Let's go back to one of the observations or comments that I made a little bit earlier, and let's bring up our power rule just for the moment. Remember that we did the integral from x to the n, and we got 1 over n plus 1 times x to the n plus 1, and we're like, oh, well, that's a little bit interesting, because the derivative of this 1 over n plus 1 times x to the n plus 1, that's just going to be equal to x to the power of m. Is that just by coincidence, or is there really something magical going on here in between this function here and this function here? So from here on, I'm going to be like, okay, well, the integral from a to b of x or some function doesn't even have to be a polynomial as long as it's continuous. Let's assume the integral from f of x dx is equal to some function here. Is it very easy to get what this function here is from this function here? Or do these functions have some relationship to each other? The beautiful answer is yes. So what I want to do is I want to sort of go through that little story with you and show you what that relation is and why that relation actually is the case. So what we're going to do is we're going to be defining a new function. I'm going to call this function f of x, capital F of x, and this is going to be defined to be equal to the integral from L to x of f of t dt. right? Here, L is just going to be a lower bound for our area. So let's assume that this is our function, little f, and let's assume that this is just some number L that's fixed, so just a fixed number. So it's a fixed number. And x is going to be somewhere over here. The axis of interest, this is going to be our t-axis, and this is going to be our f of t axis, right? So if I change my value of x, then my area will change as well, right? So if my area moves forward in this picture, then my area will accumulate to something larger. If my x moves towards L, then my area in green should be decreasing, right? So it's in some sense what a lot of people call an accumulation function. Accumulation function. Because it's a function that measures the accumulation of area underneath a curve little f from some bound to some other bound that is particularly a variable bound. And both of them could be variable bounds too, but in this case, only one of them is a variable, right? So a couple little things that we would have here, right? So if I pick a particular number b, then x will be equal to b, and that's going to give me the integral from L to b, right? So the integral from L to b of f of t dt, and I could pick another number besides b, I can call it a, and that's going to be equal to the integral from L to a of f of t dt. So that's just going to represent two different areas under the curve from L to two different numbers. So from these two things, I'm going to subtract them, and we'll see why we want to do that in just a moment. So f of b minus f of a will be equal to, from these two little statements here, the integral from L to b of f of t dt minus the integral from L to a of f of t dt. Now, I can switch these limits as long as I change the sign on that end using my limit reversal rule. So that's going to be equal to the integral from L to b of f of t dt plus the integral from a to L of f of t dt. And what I can do is I can switch these because these are just real numbers. So I can switch their order in terms of addition. So this is just going to be equal to the integral from a to L of f of t dt plus the integral from L to b of f of t dt. So if we look at a picture of what's going on here, so here's our a and L and our b. Our first integral here is going to give us the area from a to L. And then our second integral here is going to give us the area from L to b. So when we add these two integrals together, that's just going to be the integral from a to b. And let's just keep it consistent and write it just as f of t dt. So we get this very, very interesting observation that f of b minus f of a is the integral of this function little f from a to b, right? So we're building this connection between capital F and little f, right? So let's sort of summarize what we have here. So if f of x is defined to be equal to the integral from some number L to x of f of t dt, then the integral from a to b of little f of x dx will just be equal to that new function capital F evaluated at b and that new function capital F at little b. Right? So that's pretty interesting, but still remains the question, who is f? Does the capital F have a particular relation to the function little f? Right? So again, let's work with this definition of capital F and see what happens when we take the derivative of it. So the derivative of our accumulation function. So that's going to be equal to, by definition, via four difference limits, the limit as epsilon goes to 0 of capital F of x plus epsilon minus capital F of x all over our epsilon function, right? So let's work with this little definition and see if we can get anything interesting out of it. So this is going to be equal to the limit as epsilon goes to 0. Let's factor out that 1 over epsilon so we have something nice. So f of x plus epsilon, what is that? So that's the area from L to x plus epsilon of our function f of t dt. And then we're going to have minus the integral from L to x of f of t dt. And here I'm going to reverse my limits and then change my minus to a plus, just to see what that turns into. So I have the limits as epsilon goes to 0 of 1 over epsilon. And then we're going to have the integral from L to x plus epsilon of t dt plus the integral from x to L of f of t dt. And again, since these are real numbers, I can exchange these around this addition sign. So once I have that, this is going to be the limit as epsilon goes to 0 of 1 over x epsilon. And then the integral from x to L of f of t dt plus the integral from L to x plus epsilon of f of t dt. And notice this is from x to L and then from L to x plus epsilon. So these two integrals combine to the integral from x to x plus epsilon using the same logic as we did before because we're just adding two areas together to get a bigger area. So we have that the derivative of this weird function is just equal to the limits as epsilon goes to 0 of 1 over epsilon times the integral from x to x plus epsilon of our little function little f of t dt, right? It still looks a little bit weird, but we have something interesting going on here. So notice that as epsilon goes to 0, we have 0 on the bottom, and as epsilon goes to 0, this thing goes to 0 too because it goes to the integral from x to x, which we already know is 0. So this is going to be a 0 divided by 0, which as we know is just an indeterminate form. But L'Hopital's rule isn't really going to get us anywhere because yes, the derivative of epsilon with respect to epsilon is 1, but the derivative of this little integral function with respect to epsilon, that's not exactly obvious here, right? So let's see if we can geometrically interpret what this indeterminate form is going to come out to. So what we have here is some function. So this is our function f. We have x and x plus epsilon. And what we have here in this particular integral is the area underneath f on this interval, right? Now, in this picture, this epsilon is really large, right? So what I want to do is I want to make that epsilon a little bit more smaller. So once I make my epsilon a little bit more smaller, my picture is going to become a little bit more closer like this. All right, so x and x plus epsilon, where my epsilon is just a little bit more smaller. I mean, in terms of pictures, it's a lot more smaller. We're going to get this, right? So this is going to be a smaller epsilon. But one thing that you should notice that as I make that epsilon a little bit more smaller, this boundary approaches a constant horizontal boundary, like y is equal to c, right? So that means this height, which is practically guided by f of x, right? Because as epsilon gets smaller, this differential is going to go to 0, at least geometrically, because we're assuming that our function is continuous. And this distance for this almost rectangle is equal to epsilon. So as epsilon goes to 0, what we have is the following. So we have the derivative of f of x will be equal to the limit as epsilon goes to 0 of 1 over epsilon times that integral which goes to epsilon times f of x. So here our 1 over epsilons will cancel and we're just left with the derivative of capital F of x is equal to our little f of x, right? So we have that the derivative of capital F is little f. So what's the relationship in the other direction? Usually we say that capital F is the antiderivative of little f. And that is practically the connection between these two things. So now that we've proven this result between these two functions, capital F and little f. Some people will call this the fundamental theorem of calculus. Let's actually look at a variety of different functions that we explored in single variable calculus and see if we can find the areas underneath them using this very beautiful theorem. Let's do a couple examples. Example 1. Suppose we have the integral from 5 to 7 of the function 1 over x dx, and we want to find the area underneath this curve from 5 to 7. So the thing we need to do using this little theorem that we just proved is we have to know the function whose derivative is 1 over x. And as you should already know, the derivative of the natural log of x plus c function will give us that particular area. So let's plug in 7, let's plug in 5, and see what this area comes out to. So this is going to come out to the natural log of 7 plus c minus the natural log of 5 plus c. And notice that these c's are going to cancel, regardless of what those c's are. So we're just going to be left with the natural log of 7 minus the natural log of 5. And using the properties of natural logs, you can write that as the natural log of 7/5 if you prefer. So that's going to be the area underneath this particular curve. Now, before I move on to the other examples, it's very important to note that these c's will cancel regardless of those c's. So usually we take c to be equal to 0 here. Every time we're trying to find areas under curves, i.e. establish antiderivatives of 1 over x or whatever function is there, right? And again, how did we get this particular function natural log of x? Well, we answered the function, the derivative of something is equal to 1 over x, and that allows us to establish that, okay, well, from single variable calculus, we know the natural log of x plus c is that particular function. Now, let's look at a couple other examples and see if we can figure out who the antiderivative is. So let's assume we have the integral from 0 to pi of the sine function dx. So the derivative of something is equal to sine. Who is that something equal to? One should know that it's equal to minus cosine plus c. But we can take that c to be equal to 0 for the same reasons mentioned above. So that means this is going to be equal to minus cosine of x, evaluated as x goes to pi, as x goes to 0, and then we're going to subtract. So we're going to have minus cosine of pi minus cosine of 0. Make sure to keep your minus signs in parentheses in the right positions. So we're going to have, well, the cosine of pi is going to be minus 1, so we have minus 1. And then minus, and the cosine of 0 is also going to be minus 1. Or the cosine of 0 is just going to be 1. And then we're going to have minus 1 that's going to be 1, and then minus 1 is going to be positive 1. So we're just going to be left with the very friendly number 2. So that's pretty nice. So let's look at another example, example 3. Suppose we have the integral from 0 to 1 of 1 divided by 5x plus 2 dx. So we have 1 divided by a linear function, and we know that logarithms will generate such things. Now that 5 via the chain rule needs to eliminate, so we need to bring in a 1 over 5 there. So 1 over 5 times the natural log of 5x plus 2 plus c would be the antiderivative of 1 over 5x plus 2. And now we need to evaluate this function as x goes to 1, as x goes to 0, and then we're going to be subtracting those values from each other. So this constant can factor out if we want it to, so we can write this as 1/5 just to make things a little bit more nicer to deal with. And then we're going to have the natural log of 5 times 1, which is 5 plus 2 is 7. And then minus the natural log of 5 times 0 is 0 plus 2 is 2. So we're going to have 1/5 times the natural log of 7/2 as our answer. And that's the area underneath this particular friendly little curve. And let's just do another example just to see if you remember. Example 4, the area from 0 to 1, 1 over 1 plus x squared dx. So this is a very special derivative rule that you should remember, because the derivative of the arctangent function will give you 1 over 1 plus x squared. Now we need to evaluate it 1, evaluate it 0, and subtract. So once we do that, we're going to have the arctangent of 1 minus the arctangent of 0. And that's going to be equal to what? So the arctangent of 0 we know is going to be 0, and the arctangent of 1 occurs when sine and cosine are equal to each other, because tangent is sine divided by cosine. So when is sine and cosine equal to each other in the interval 0 to pi, you should know that that's going to be equal to the 45-degree angle, aka pi over 4. So that's how you can find definite integrals if you can observe or know the antiderivative of the function just based on your single variable calculus knowledge. Now, these examples are perfectly fine if you can observe or remember the identities for which these functions anti-differentiate to, but there are actually infinitely many, and actually even more functions that you don't know the answer to, due to a lot of theory that we'll talk about at a little bit later time. One of them functions is what is called the sine integral function, which I'm going to denote as capital S of little I of x, which is defined as the integral from 0 to x of the sine of t over t dt. So why are we defining the integral of the sinc function as a function of its own? Because if we want to take the integral of the sine x over x of the sinc function, you have to guess, well, the derivative of who is equal to the sinc function. And you think for, several minutes, several hours, several days, several years, several generations, and you can't think of any, at least in terms of functions that you don't know. And that's because there isn't one, right? Now, how to prove that very weird result, that will come at a later time. We need a little bit more theory to handle that question. But take my word for it, you won't be able to find one, so we have to define it if we want to use it. Its definition is psi of x, so the sine integral of x, right? So what is the derivative of the sine integral of x equal to? So what is the derivative of this integral defined function? So the derivative of this thing, right? Now, do we know what the derivative of sine of t over t is, where we can plug in t is equal to x, t is equal to 0, and evaluate? Probably no. So what we're going to do is we're going to call it capital F. Now, it does have the name psi of x, but let's just set that aside for just a moment. So we're going to call the antiderivative of sine t over t to be f, right? So therefore, the derivative of f of t with respect to x, let's say, will be equal to the sine of x over x. All right? So if that's the case, then what we're going to have here is the derivative of f of t, and then we're going to evaluate that as t goes to x and as t goes to 0. So we're going to have the derivative of f of x minus f of 0. So we can distribute derivatives because derivatives are linear operators, and we're going to have the derivative of f of x minus the derivative of f of 0. But remember, f of 0 is just a number, so this is going to disappear to 0, and we know that the derivative of capital F of x is equal to sine x by definition. Right? So we have that the derivative of the sine integral of x is equal to the sine of x over x, which we shouldn't be surprised because psi of x is defined as the antiderivative of sine of t over t. Therefore, we get this. So if you ever come across a problem where they're like, oh, what is the integral of sine of x over x from, like, say, 1 to 7 of dx, you can just say, okay, well, that's just the sine integral evaluated as x goes to 7 and as x goes to 1. And that's just going to be psi of 7 minus psi of 1. And then there's methods to figure out what that approximately is equal to via some decimal expansions, which we'll discuss a little bit later. So let's just do another example of these integral defined functions, because these are definitely going to be very important a little bit later on. So what is the derivative of the integral from x squared to the sine of x of the sine of t squared dt? Right? So the first thing we would have to figure out is, okay, well, what is the antiderivative of the sine of t squared? And again, this does not have a cute answer, so we need to call it a name. Let's just call it f for now. So if it is equal to f, that means this is just going to be equal to the derivative of f of t, and then we're going to evaluate this as t goes to the sine of x, and as t goes to x squared. So once you have that, that's going to give us the derivative with respect to x of f of sine of x minus f of x squared. Derivatives are linear operators, so we can distribute that over. So we're going to have the derivative of f of sine of x, which is definitely a function composition. And then we're going to have f of x squared. Now we're going to apply the chain rule because we know how to define these functions or differentiate compositions of functions. So it's the derivative of the outside times the derivative of the inside, and the derivative of sine, which we know is going to be cosine, and then minus the derivative of f evaluated at x squared times the derivative of x squared, which is 2x. Now, what is the derivative of f of x? Well, that's just going to be equal to the sine of x squared using the same logic as before. So that means this is going to be equal to the sine of the inside squared times cosine of x, and then minus the sine of something squared, which is, I guess, going to be x to the fourth, times 2x. And that would be your answer, which I think is quite nice. So those things that we've discussed today are definitely fundamental theorems that you definitely should understand when it comes to definite integrals, in particular the fundamental theorem of calculus. This little theorem here, where we're taking derivatives of integral defined functions, sometimes is referred to the fundamental theorem of calculus part 2. But nonetheless, it's just an application of antiderivatives, which are just functions whose derivatives are the functions that you're trying to integrate over. And obviously they have that beautiful connection to find areas underneath curves. But keep in mind, not all functions have these things called elementary derivatives or elementary antiderivatives, where it can at least express it in terms of functions that you already know. More on that later. So I hope you enjoyed this video, and I'll see you in the next one. Take care.